this video clip, we see that the vehicle launched off of the top of the parking structure is experiencing projectile motion. In order to determine the plausibility of its motion and whether or not it will truly land reasonably at the juncture between the next building and the sidewalk, we must consider several physical factors of the scene. The first of these factors is the height of the launching point, represented by y. This affects the rate of fall based on how much velocity the vehicle can accumulate through acceleration of gravity before landing. The second dimensional factor is the width of the gap that the vehicle must cross. Though the vehicle remains at a constant horizontal velocity, it is important to determine how far it must cross in the time period given by the gravitational acceleration. The final two factors of this scene, which are the time and the initial velocity, can be calculated if the height and the width are found. In order to find these measurements, we can rely on several environmental details that demonstrate that this clip was filmed in Germany. The statement of filming locations confirms this fact as well. After finding the exact location of this scene, we can evaluate the height of the buildings. In Europe, an average story is approximately 3 meters tall, and these buildings each have 6 stories. Therefore, these buildings can be surmised to be nearly 18 meters in height. Finding the width of the gap can also be done through environmental factors. In this region, there is a great number of European transport buses. Lane size regulations dictate that most buses must be exactly 2.5 meters in width, and since this area is nearly 7 bus lengths wide, 17.5 meters serves as an initial estimate of its width. In addition, we must consider the distance between lanes, approximately 0.16 meters. After full calculation, the roadway and sidewalk end up measuring approximately 18.4 meters across. Therefore, we can apply these values to the original scene and move to the next step of calculation.
First, we need to find the time it takes for the car to go from the top of the building to the ground. To do this, we can use the equation y equals v0t plus 1/2 at squared. Since the y component of the initial velocity is 0, we can simplify it into 18 meters equals 1/2 times 9.8 meters per second squared times t squared. We can simplify this into t squared equals 3.6734 seconds squared, and we get t equals 1.9 seconds, which rounds to 2 seconds. Now that we know the time it takes, we can find the initial horizontal velocity. We can use the same equation, and we know that t equals 2 seconds. Since the acceleration is 0, we can simplify the equation to 21 meters equals v0 times 2 seconds plus 0. This gives us an initial velocity of 10.5 meters per second.
The calculations find that the initial velocity of the vehicle must be 10.5 meters per second and that the time of its fall is 2 seconds. These are reasonable measurements that are attainable within the context of the scene. Therefore, in this manner the scene is plausible. However, we do not take into consideration factors such as drag, spring force of suspension upon landing, and integrity of structural features, including liability of explosion through the gas tank. In the simplest terms of kinematics, this stunt is plausible. However, there is one last aspect of the scene for us to consider. Though we have found the calculations to be accurate, the image shown is incorrect. The vehicle is at far too shallow of a fall to land on the first story. Its projected angle of path would have crashed it into the second or third stories, thus disregarding the measurements that we have calculated.
Congratulations on a safe journey.